Picture this. You're standing at the edge of a vast, uncharted ocean, looking out at an endless expanse of possibility. Now, imagine that ocean is the cosmos, and everything we thought we knew about its depths, its currents, and its very nature is being called into question. What if the universe isn't quite as we've been taught to understand it? What if the seemingly solid foundations of our cosmological models are beginning to crack under the weight of perplexing, undeniable evidence? This isn't science fiction. This is the cutting edge of cosmic discovery, where the universe itself is sending us signals that defy our neatest equations and most elegant theories. It's a journey into the truly unknown, a thrilling intellectual adventure that beckons us to challenge our deepest assumptions about reality. In this video, we're not just going to scratch the surface, we're diving headfirst into 28 mind-bending anomalies that are reshaping cosmology forever. Think of them as cosmic riddles, each one a tiny crack in our comprehensive understanding, revealing glimpses of a universe far stranger and more complex than we ever dared to imagine. From the most fundamental particles that make up existence to the largest structures spanning billions of light years, these puzzles are forcing scientists around the globe to redraw the cosmic map. They challenge everything from the accelerating expansion of the universe to the very existence of matter, pushing the boundaries of scientific thought and demanding that we open our minds to possibilities once considered impossible. Prepare to have your perception of the cosmos fundamentally stretched as we explore observations that simply do not fit into our current understanding. These aren't just minor inconsistencies, they are profound discrepancies that could point to entirely new laws of physics, forces, or even dimensions. This isn't just a list of strange facts. It's an invitation to join us on an exhilarating expedition to the very edge of known science. We'll delve into the mysteries that keep cosmologists awake at night, those stubborn observations that refuse to conform, pushing the boundaries of human knowledge and reminding us just how much more there is to learn about the grand cosmic tapestry. Each anomaly we explore promises to challenge conventional wisdom, opening new avenues of thought about our place in this vast, enigmatic universe. As we unravel these enigmas, you'll discover that the most exciting questions in science are often the ones we can't yet answer. So, buckle up for a journey that will not only illuminate the universe's strangest secrets, but also inspire awe for the sheer scope of the unknown. Our exploration begins by setting the stage for these extraordinary scientific challenges, starting with the perplexing case of the Pioneer Anomaly. Our journey into the cosmos's most baffling mysteries begins not light years away, but right here in our own cosmic backyard, with something known as the Pioneer Anomaly. Imagine for a moment two intrepid robotic explorers, Pioneer 10 and Pioneer 11, launched by NASA back in the early 1970s. These spacecraft were designed for grand voyages, heading out to the gas giants, Jupiter and Saturn, before continuing their lonely trek out of our solar system, destined to explore the vast emptiness of interstellar space. For decades, as these probes journeyed ever further, scientists meticulously tracked their every movement, expecting them to follow the precise, predictable laws of gravity laid out by Isaac Newton and later refined by Albert Einstein. But something peculiar began to emerge from the data, a subtle, persistent whisper in the cosmic silence. Both Pioneer 10 and Pioneer 11, without any obvious cause, started to experience a tiny, uncommanded acceleration. This wasn't a sudden jolt, but a minuscule, consistent push back towards the Sun, a force so small it amounted to less than a billionth of the Earth's gravity, yet it was undeniably there. Think of it like this: if you were driving a car and it was constantly, ever so slightly, tapping the brakes without you touching the pedal, eventually that little tap would add up to a significant, unpredicted slowdown. For the Pioneer spacecraft, this meant they were always a little bit closer to the Sun than our best models predicted they should be. Scientists, always rigorous in their pursuit of truth, left no stone unturned in trying to explain this persistent drift. Was it something mundane, like heat radiating unevenly from the spacecraft's power source, creating a tiny propulsive force? They checked. What about small gas leaks from the thrusters, pushing the probes off course? Investigated, could it be errors in the instruments themselves, or even the subtle pressure from sunlight reflecting off the spacecraft? Every conventional explanation was painstakingly analyzed, modeled, and re-evaluated. Yet, even after years of exhaustive scrutiny, including a detailed re-analysis of the telemetry data from both missions, no standard physical phenomenon could fully account for the observed acceleration. This is why it's such an anomaly. It's not just a minor observational hiccup. It defies all known physics in a way that suggests something more profound is at play. The fact that it affected both spacecraft in a similar way, behaving as if an unknown force was subtly tugging them, has led some to speculate about truly revolutionary possibilities. Could this tiny, unexplained acceleration be an early, faint signal of new physics operating on the fringes of our solar system? Perhaps it hints at a fundamental flaw in our understanding of gravity itself, a force that behaves differently over vast cosmic distances than we currently perceive. Or, even more intriguingly, it might be the first clue to a previously unknown force, something entirely new to our cosmic rulebook, hinting at physics beyond the standard model that governs the known universe. The Pioneer anomaly serves as a potent reminder that even our most distant and seemingly simple probes can reveal the universe's most unexpected secrets, prompting us to ask, what other invisible forces are shaping the cosmos that we are yet to discover? Just as we grapple with the mysterious push on the Pioneer probes, another equally perplexing anomaly crops up much closer to home, the Flyby anomaly. Imagine spacecraft, instead of heading out to the far reaches of the solar system, are simply swinging by Earth, using our planet's gravity to get a speed boost, a kind of cosmic slingshot maneuver. Now, these gravity assists are crucial for many missions, saving fuel and time by harnessing the immense gravitational pull of a planet to alter a spacecraft's speed and trajectory. Engineers calculate these maneuvers with incredible precision, factoring in every known variable down to the most minute detail. Yet, for missions like Galileo, which explored Jupiter, near Shoemaker, which rendezvoused with an asteroid, Rosetta, the comet chaser, and Cassini, the Saturn orbiter, something consistently went awry. During their close Earth flybys, these spacecraft, along with others, exhibited tiny, unpredicted accelerations. It wasn't a huge deviation, but a small, consistent gain or loss in velocity that simply couldn't be explained by our current physics. Think of it, a spacecraft is supposed to come out of a gravity assist at a very specific speed, but repeatedly, missions would emerge just a little bit faster or slower than calculated. This wasn't random noise in the data. It was a noticeable, systematic error that engineers painstakingly tried to account for. Just like with the Pioneer anomaly, every conventional explanation was thoroughly investigated. Could it be a subtle drag from Earth's upper atmosphere, even at extreme altitudes? What about the tidal forces exerted by the Earth and Moon, or even the minuscule pressure from sunlight? All these factors were modeled and re-examined, but none could fully explain the consistent, tiny velocity changes observed across multiple, independent missions. The fact that different spacecraft, built by different teams for different destinations, all experienced similar unexplained effects during their Earth flybys makes the puzzle even more intriguing. It points away from a simple engineering glitch and towards something more fundamental. This persistent pattern suggests either an unknown gravitational effect, a subtle relativistic phenomenon we haven't quite grasped, or perhaps an interaction with some other unknown force at play during these high-speed, close approaches to a massive body like Earth. It directly challenges our most precise gravitational calculations, hinting that our understanding of how gravity behaves in these specific cosmic dance sequences might be incomplete. The Flyby anomaly, much like the Pioneer anomaly, serves as a powerful reminder that even in our well-charted solar system, fundamental physics might still hold secrets, forcing us to reconsider the very mechanics of how objects move through the cosmos. Could it be that our gravitational rulebook needs another chapter, or even a complete rewrite? Moving from the puzzling flight paths of spacecraft, we now plunge into one of cosmology's most enduring and perplexing enigmas: dark matter. For decades, scientists have grappled with the undeniable evidence of its existence, which, ironically, comes only from its invisible hand. We can't see it, touch it, or even directly detect it, yet its gravitational effects are profound and pervasive, shaping the very structure of the cosmos. Think of it this way: when we observe galaxies spinning, their outer stars are moving far too fast to remain gravitationally bound by the visible matter alone. It's as if an invisible, massive scaffold holds them together, preventing them from flying apart. This gravitational signature provides compelling proof that there's far more mass out there than meets the eye. What exactly is this unseen substance? The universe, as we understand it, is composed of different forms of energy and matter. Visible matter, the stuff that makes up stars, planets, and us, accounts for only about 5% of the cosmos. Dark matter, on the other hand, is estimated to make up a staggering 27% of the universe's total mass energy content. This means that for every handful of ordinary matter, there are more than 5 times as much dark matter surrounding it. Despite its overwhelming presence, its true nature remains one of the greatest unsolved mysteries in science, a ghost in the cosmic machine that defies all attempts at direct observation in laboratories here on Earth. Scientists have built incredibly sensitive detectors deep underground, hoping to catch even a fleeting interaction with a dark matter particle, but so far, the results have been consistently negative. The implications of this invisible component are enormous. Dark matter isn't just a minor puzzle, it's a cornerstone of our modern cosmological model. Without it, our theories about how galaxies form, how galactic clusters hold together, and even how the large-scale structure of the universe evolved simply don't work. It acts like the cosmic glue that holds everything together, guiding the formation of the vast cosmic web of galaxies and clusters. But because we can't directly observe it, its very identity poses a profound challenge to our understanding of the universe's fundamental composition. If we don't know what the majority of the universe is made of, how can we truly claim to understand it? This leads to a truly revolutionary question. What if dark matter isn't a particle at all, but rather a manifestation of modified gravity, a subtle tweak to Einstein's theory that explains these gravitational anomalies without needing a new, exotic substance? This idea, while provocative, opens up entirely new avenues for how we might rewrite the cosmic rulebook. While dark matter presents a profound challenge, making up a significant chunk of the universe's mass, an even more perplexing enigma dominates the cosmic landscape: dark energy. This extraordinary component is estimated to constitute a staggering 68% of the universe's total mass energy content, far outstripping even dark matter. If dark matter acts as the gravitational glue holding things together, dark energy, in stark contrast, is the universe's engine of accelerated expansion, pushing everything apart at an ever-increasing rate. Imagine a balloon with dots on its surface representing galaxies. If you start blowing it up, the dots move away from each other. Now, imagine something inside the balloon that makes it inflate faster and faster over time. That's essentially what dark energy seems to be doing to our universe. The discovery of this accelerated expansion in the late 1990s stunned the scientific community. Before then, the prevailing idea was that the universe's expansion should be slowing down due to the cumulative gravitational pull of all matter within it. Finding that it was speeding up rewrote the cosmological textbook overnight, introducing a force unlike anything we had ever conceived. But what exactly is this mysterious force? Its nature remains one of the greatest unsolved problems in all of physics, prompting a diverse range of theories that attempt to explain its origin and behavior. One leading idea is that dark energy is simply a cosmological constant, a concept first introduced by Albert Einstein, who later called it his biggest blunder when he thought the universe was static. If he had only known then what we know now, he might have seen it as his greatest triumph. This constant would represent the intrinsic energy of empty space itself, a force that doesn't dilute as the universe expands. Another compelling theory posits that dark energy isn't constant at all, but rather a dynamic, ever-changing field known as quintessence. Think of it like a fifth fundamental force, a pervasive energy field that permeates all of space but whose strength and properties can evolve over time. This idea opens up fascinating possibilities, suggesting that the rate of cosmic expansion might not always be what it is today and could even change again in the distant future. The implications of dark energy are not merely academic, they are profound, raising fundamental questions about the ultimate fate of the cosmos. Will the universe continue to accelerate its expansion indefinitely, leading to a big rip where even atoms are torn apart? Or will dark energy eventually dissipate, allowing gravity to reassert itself and leading to a big crunch? The answers to these questions are deeply intertwined with the true nature of dark energy. Is this pervasive, accelerating force a temporary phase in the universe's long history? Or is it a fundamental, unchanging property of spacetime itself, dictating the very fabric of our reality? Understanding dark energy is key to unlocking the universe's ultimate destiny. While dark energy stretches the cosmos, driving its expansion at an ever-increasing clip, another cosmic puzzle creates a different kind of tension for scientists, the Hubble tension. This anomaly isn't about what's pushing the universe apart, but how fast. Specifically, it involves a stubborn and significant disagreement over the precise value of the universe's expansion rate, a value known as the Hubble constant. Think of the Hubble constant as the universe's speed limit, telling us how quickly a galaxy at a certain distance is moving away from us. For decades, astronomers have been trying to pin down this number with increasing precision, but recently, two primary methods of measurement have started giving us noticeably different answers, creating a cosmic conundrum that refuses to be ignored. One way to measure the Hubble constant involves looking at the very early universe, specifically at the cosmic microwave background, or CMB. This ancient light, often called the afterglow of the Big Bang, provides a snapshot of the universe when it was just 380,000 years old. By studying the tiny temperature fluctuations in the CMB, scientists can infer the initial conditions of the universe and, using our best cosmological model, the lambda CDM model, predict what the current expansion rate should be. It is like looking at a baby photo and predicting how fast that person will be running as an adult based on their initial growth spurt. This method consistently calculates a lower value for the Hubble constant, suggesting a slower expansion rate. However, when scientists measure the Hubble constant using more local, direct observations of the present-day universe, they get a different answer. This involves observing distant supernovae, which are exploding stars that act as standard candles because their intrinsic brightness is known, allowing astronomers to calculate their true distances. Another tool in this cosmic toolkit is the use of Cepheid variables, pulsating stars whose luminosities are directly related to their pulsation periods, similarly serving as reliable cosmic yardsticks. By combining these distance measurements with observations of how fast these galaxies are receding from us, scientists can directly calculate the universe's expansion rate today. It is like measuring how fast an adult is actually running right now. This local measurement consistently yields a higher value for the Hubble constant, implying the universe is expanding faster than the CMB data predicts. The persistent 8 to 9% difference between these two sets of measurements is far from a trivial discrepancy. It significantly exceeds the statistical uncertainties in either method. This tension is not simply a matter of slightly different numbers. It strikes at the heart of our most successful cosmological model, the lambda CDM model. If both measurements are correct, it would suggest a fundamental flaw in our understanding of the universe's evolution or its basic composition. It's like having two perfectly calibrated clocks that, despite all logic, tell you two slightly different times, and you can't figure out why. Is one of the clocks wrong, or is there something fundamentally different about how time works for each? Resolving this Hubble tension might very well require new physics beyond our current cosmological paradigm. It could mean that there are unknown errors in our measurements, though scientists have painstakingly checked and rechecked their data, or it could point to entirely new particles, forces, or even a modification to gravity itself. Perhaps dark energy isn't as simple as we think, or there's some other component influencing the early universe that we haven't accounted for. This cosmic conundrum indicates a potential shift in our fundamental understanding of universal expansion and how the cosmos has evolved since the Big Bang. The implications of this tension ripple through our entire cosmological framework, urging us to question whether our current map of the universe is missing crucial territories. Moving from the grand scale of cosmic expansion, let us now zoom in on something seemingly small but equally perplexing, the lithium problem. This anomaly takes us back to the universe's earliest moments, just minutes after the Big Bang, when conditions were so hot and dense that atomic nuclei could form. Our most successful model for this period, known as Big Bang nucleosynthesis, or BBN, beautifully predicts the abundances of the lightest elements like hydrogen and helium. For example, it gets the ratio of hydrogen to helium almost perfectly right, which is a huge triumph for cosmology. However, when it comes to lithium-7, the story changes dramatically. According to BBN theory, the early universe should have produced a certain amount of lithium-7. But when astronomers measure the amount of lithium in the oldest stars, which act as cosmic time capsules preserving the pristine chemical composition of the early universe, they find significantly less of it, sometimes by a factor of 3 or even 4. This isn't a small margin of error, it is a persistent discrepancy, a glaring mismatch between what our best theory predicts and what observations show. It is like having a recipe that works perfectly for every ingredient except one, leaving you scratching your head about what went wrong with that single, stubborn component. This stubborn discrepancy, often referred to as the cosmological lithium problem, has been a thorn in the side of cosmologists for decades, frustrating efforts to achieve a complete picture of the universe's infancy. Scientists have explored numerous possibilities to explain this missing lithium. One line of thinking suggests that the problem lies within our understanding of BBN itself. Perhaps some of the input parameters, like the exact density of ordinary matter in the early universe, are slightly off. Or maybe there were exotic nuclear reactions not accounted for in our models that either destroyed primordial lithium or prevented its formation in the first place. Another intriguing possibility points to new particle physics beyond the standard model. Could new, undiscovered particles have interacted with the early cosmic plasma, influencing the nucleosynthesis process in unexpected ways? For instance, certain hypothetical particles could have decayed after BBN, releasing energy that either destroyed lithium nuclei or altered the conditions for their formation. This would imply a profound connection between the very smallest building blocks of reality and the largest cosmic structures, linking particle physics to the grand narrative of the universe's chemical evolution. Resolving the lithium problem is not just about correcting a minor detail. It could have far-reaching implications for our understanding of the universe's initial conditions and the fundamental laws that govern it. If the problem stems from BBN theory, it would mean we need to refine our understanding of the universe's first few minutes, perhaps even revising the precise timeline of events after the Big Bang. If new particle physics is the answer, it would open up a whole new realm of discovery, pointing towards exotic particles or interactions that we are yet to detect. It is a compelling example of how a seemingly small anomaly can force us to re-examine the foundational assumptions of our cosmic models, potentially redefining the cosmic blueprint and shedding light on the exotic physics that govern the earliest moments of our universe. The search for the missing lithium continues to drive research, pushing the boundaries of both nuclear physics and observational astronomy, reminding us that even the most well-established theories can still hold surprises. Stepping away from the cosmic crucible of the early universe, let's shift our focus to something much closer to home, yet equally perplexing: the mystery of the KBC Void. Imagine looking up at the night sky, billions of galaxies twinkling like scattered diamonds. Our own Milky Way galaxy is just one of them, nestled within what we understand as the grand cosmic web, a vast, intricate network of galaxy clusters and filaments separated by immense, relatively empty regions called cosmic voids. While these voids are a standard feature of the universe's large-scale structure, the one we find ourselves in stands out as unusually large and remarkably empty. This exceptional region is formally known as the Keenan, Barger, and Cowie, or KBC Void, and it stretches for hundreds of millions of light-years, encompassing our galaxy and many of our nearest galactic neighbors. It's not just that we are in a void, it's the sheer scale of its emptiness that poses a puzzle. According to our standard cosmological model, the universe should be relatively uniform on very large scales, a principle known as cosmic homogeneity. However, the KBC void size and its relatively low density of matter present a statistical anomaly, seemingly challenging this fundamental assumption. It's like finding ourselves living in the middle of a vast, empty prairie when all the maps suggest we should be in a bustling metropolis. The existence of such a large local underdensity has significant implications, particularly for the ongoing debate surrounding the Hubble tension. Remember how the Hubble tension refers to the discrepancy in the universe's expansion rate measurements. Well, some scientists propose that the KBC void could offer a potential explanation for this. If our local cosmic neighborhood is indeed a vast, empty bubble, the gravitational pull from the denser regions outside this void could be influencing our measurements of the universe's expansion. This local gravitational effect might cause us to perceive a different expansion rate compared to measurements derived from the early universe, which average over much larger scales. In essence, our neighborhood's unique cosmic geography could be subtly distorting our view of the universe's overall expansion. This possibility challenges our assumptions about how truly homogeneous the universe is on all scales. If our local environment significantly deviates from the cosmic average, it could mean our understanding of cosmic flows and the distribution of matter needs refinement. It prompts us to consider whether our local cosmic address is far more unique than previously thought, potentially influencing fundamental cosmological measurements. The KBC Void encourages us to look not just at how the universe expands, but also at the impact of our own cosmic backyard on those measurements, reminding us that even in the vastness of space, location can influence perception. Beyond the Hubble tension and the peculiarity of our cosmic neighborhood, another profound challenge to our understanding of the universe emerges from the cosmic microwave background itself. Imagine, if you will, the very first light in the universe, a faint glow released some 380,000 years after the Big Bang. This ancient light, known as the cosmic microwave background, or CMB, acts like a baby picture of our cosmos, containing crucial information about its early structure and evolution. Scientists have painstakingly mapped its tiny temperature fluctuations across the entire sky, seeking to confirm our cosmological models. However, when they peered closely at these maps, particularly at the largest scales, a truly unsettling pattern began to emerge, something so unexpected it was quickly dubbed the axis of evil. This provocative name refers to the fact that certain large-scale temperature variations in the CMB, specifically the quadrupole and octopole moments, which represent the broadest patterns of hot and cold spots, appear to be strangely aligned with each other. Even more bizarrely, these alignments seem to line up with the plane of our solar system, known as the ecliptic. Now, why is this so problematic? Our standard cosmological model is built on the cosmological principle, a fundamental assumption that on sufficiently large scales, the universe is homogeneous and isotropic. In plain language, this means the universe should look roughly the same in all directions, with no preferred position or direction. The axis of evil directly contradicts this, suggesting a hidden, preferred orientation in the universe, or perhaps an artifact in our measurements that we haven't yet accounted for. The implications of this axis are truly unsettling. If it's a real feature of the cosmos, it means the universe isn't as uniform as we thought. It could suggest that the early universe wasn't as perfectly smooth as our models predict, perhaps hinting at exotic physics at play immediately after the Big Bang, or even a universe that is not infinite in extent but rather has some peculiar topology. On the other hand, if it turns out to be a measurement artifact, it means there's something fundamental about our observational techniques or data processing that we don't fully grasp. Perhaps unknown foreground emissions are subtly contaminating our signal, or there's an unexpected systematic error in how we collect or interpret the data. Regardless of its origin, the axis of evil forces us to confront some uncomfortable truths. It challenges the very foundation of our cosmological principle, a cornerstone of modern astrophysics. It's like finding a mysterious, persistent compass pointing in a single direction within a supposedly directionless space. This anomaly pushes the boundaries of our current understanding, prompting deeper investigations into the universe's initial conditions and the subtle intricacies of its large-scale structure. It serves as a powerful reminder that even our most robust models can harbor hidden surprises, hinting that the universe might have a cosmic orientation we are only just beginning to perceive. Adding to the cosmic riddle posed by the axis of evil, yet another perplexing feature emerges from the cosmic microwave background, the cold spot. Imagine peering across the vast expanse of the early universe, where the cosmic microwave background reveals subtle temperature variations. Most of these variations are small, random fluctuations, precisely what our standard cosmological models predict. However, in one particular direction, there is a sprawling, unusually cold region of the sky, extending across billions of light years. This cold spot stands out like a solitary, freezing island in an otherwise uniformly warm cosmic ocean, an anomaly so vast and so cold that it challenges the very predictions of how such fluctuations should behave. The sheer size and temperature deficit of the cold spot are difficult to reconcile with our understanding of cosmic evolution. While the most straightforward explanation posits it as a supervoid, an enormous region of space with a significantly lower density of galaxies and matter than average, even this explanation struggles to fully account for its extreme coldness. A supervoid would cause a slight cooling effect on the cosmic microwave background photons as they pass through it, but the observed temperature drop in the cold spot is far more pronounced than what even the largest known supervoid should produce. This discrepancy suggests that something more profound might be at play, pushing the boundaries of what our current models can explain. Some scientists have ventured into the realm of exotic physics to explain this cosmic chill. One intriguing hypothesis involves the concept of a cosmic texture, a type of topological defect formed in the very early universe, similar to faults or cracks in the fabric of spacetime itself. Such a texture could have gravitationally imprinted a large-scale cold region onto the cosmic microwave background. Another, even more speculative, idea suggests that the cold spot might be evidence of a collision with a parallel universe, a theoretical bubble that our universe might have bumped into in its infancy. While these ideas sound like science fiction, they highlight the extraordinary nature of this anomaly and the lengths to which scientists are willing to go to understand it. The presence of the cold spot, regardless of its ultimate cause, significantly challenges the statistical uniformity we expect from the Big Bang's afterglow. Our standard cosmological model, the lambda-CDM model, is built on the assumption that the initial conditions of the universe were statistically isotropic and homogeneous on large scales. The cold spot, much like the axis of evil, directly contradicts this assumption by showcasing a massive deviation that is statistically improbable. It suggests that either our understanding of initial conditions or the subsequent evolution of cosmic structures needs significant revision. The universe, it seems, continues to surprise us with its large-scale mysteries, urging us to look beyond the familiar and explore the truly unexpected. Moving on to another perplexing cosmic phenomenon, we encounter the mystery of ultra-high-energy cosmic rays, or UHECA. Imagine particles from space hitting Earth with energies equivalent to a tennis ball traveling at 100 miles per hour, but concentrated into a single subatomic speck. Cosmic rays are essentially atomic nuclei, mostly protons, that travel through the cosmos at incredible speeds. Most of them are relatively low energy, originating from events within our own galaxy, like supernova. But then there are the UHECA, which arrive on Earth carrying energies that defy our current physics. The real puzzle begins when we consider the Greisen-Zatsepin-Kuzmin, or GZK, limit. This is a theoretical maximum energy that cosmic rays should possess if they originate from distant sources, particularly those beyond about 160 million light-years away. The reason for this limit is interactions with the cosmic microwave background. As these incredibly energetic particles traverse the vast cosmic distances, they should lose energy by colliding with the omnipresent photons of the cosmic microwave background radiation. Think of it like a baseball slowing down as it plows through a dense fog. So, if a cosmic ray starts out with an extremely high energy far away, by the time it reaches Earth after billions of years of travel, its energy should be significantly depleted. Yet, observations have consistently detected super-GZK particles that arrive on Earth with energies far exceeding this theoretical limit. This presents a profound dilemma. If these particles truly originate from distant active galactic nuclei or other powerful cosmic accelerators, then our understanding of how particles interact with the cosmic microwave background must be fundamentally flawed. It would imply that the universe is far more transparent to these extreme energies than we currently believe, which could open up entirely new avenues for understanding light and matter interactions across cosmic scales. Alternatively, the existence of these super-GZK cosmic rays could point to an entirely different scenario, that their sources are much closer to home than we initially thought. If these powerful accelerators are within a few tens of millions of light years from Earth, then the particles wouldn't have sufficient time or distance to undergo enough energy dissipating interactions with the cosmic microwave background. This would mean that our local cosmic neighborhood harbors powerful and as yet undiscovered sources capable of launching particles with such phenomenal energies, perhaps even some we haven't properly characterized. Pinpointing these potential nearby accelerators becomes a crucial task, pushing the boundaries of our astrophysical detective work. Beyond these two main possibilities, the enigma of ultra-high-energy cosmic rays also hints at the potential for entirely new physics. Perhaps there are exotic processes unknown to us that can accelerate particles to these energies, or maybe the particles themselves are not what we expect. Could they be composed of dark matter particles? Or might there be entirely new particles that interact differently with the fabric of spacetime, allowing them to bypass the conventional energy loss mechanisms? Their very existence challenges the completeness of the standard model of particle physics, suggesting that our current understanding of fundamental forces and matter might be missing a crucial piece, especially at these extreme energetic scales. The question of where such incredible energies could be coming from continues to be one of the most compelling and baffling anomalies in modern cosmology, urging us to look beyond conventional explanations and embrace the truly unknown. Transitioning from particles of extreme energy, we now turn our attention to signals of extreme brevity, the enigma of fast radio bursts, or FRB. Imagine tuning into a cosmic radio station and suddenly, a millisecond-long burst of energy, more powerful than 500 million suns, screams across billions of light years before vanishing without a trace. These aren't just faint whispers from the cosmos. They are powerful, fleeting radio emissions that have puzzled astrophysicists since their accidental discovery in 2007. While hundreds of these events have now been logged, their precise origins remain one of the most compelling unsolved mysteries in astronomy. What makes FRBs so perplexing is their incredibly short duration combined with their immense power. Lasting just a few thousandths of a second, these bursts indicate an incredibly compact source, but one capable of generating energy outputs that defy easy explanation. Initially, every FRB detected seemed to be a one-off event, flickering into existence and then disappearing forever. This led to theories involving catastrophic cosmic events, like the final collapse of neutron stars into black holes. Such events would certainly release colossal amounts of energy, but they would only happen once. However, the plot thickened with the discovery of repeating FRBs. In 2016, astronomers detected FRB 12-1102, the first burst to repeat from the same location. This single observation completely changed the game. A repeating source couldn't be a one-time cataclysmic event. It demanded an explanation involving an object that could repeatedly generate such extreme bursts of energy, hinting at a more stable, albeit incredibly powerful, celestial engine. This distinction between repeating and non-repeating FRBs adds another layer of complexity, suggesting there might be multiple types of sources or formation mechanisms contributing to the observed population. Scientists are exploring a wide array of theories to explain these cosmic flashes. One leading candidate for repeating FRBs is a type of neutron star known as a magnetar. These are incredibly dense stellar remnants, similar to black holes but with intensely powerful magnetic fields, billions of times stronger than anything we can produce on Earth. The immense stresses and strains within a magnetar's crust or powerful flares erupting from its surface could generate the kind of energy seen in FRBs. In fact, a handful of FRBs have now been directly traced to magnetars within our own galaxy, lending strong support to this hypothesis for at least some of these events. Yet, magnetars don't account for all FRBs, especially those that don't repeat or those originating from vastly different galactic environments. Other hypotheses extend into truly exotic territory. Some theories propose FRBs might be signals from interactions with dark matter, where unknown particles or fields could suddenly convert energy into radio waves. Or perhaps, and this is a more speculative but fascinating idea, they could be technosignatures, beacons, or signals from advanced alien civilizations. While the vast majority of scientists lean towards natural astrophysical explanations, the sheer power and mysterious nature of FRBs keep open the possibility of something truly extraordinary at play. These fleeting signals, representing an entirely new class of cosmic event, continue to push the boundaries of our astrophysical understanding. Delving deeper into the universe's inventory, we encounter another significant puzzle, the case of the missing ordinary matter, often referred to as the missing baryons problem. Imagine taking a cosmic census. Based on our most precise measurements from the early universe, particularly the faint afterglow of the Big Bang captured by the cosmic microwave background, and observations of the large-scale structure of galaxies, we have a clear expectation for how much ordinary matter, protons and neutrons, should exist. This baryonic matter is the stuff that makes up everything we can directly see or interact with, from stars and planets to gas clouds and dust. However, when we meticulously count all the visible matter in stars, galaxies, and the hot, X-ray emitting gas within galaxy clusters, we come up short. A significant fraction, roughly half of the expected ordinary matter, simply isn't where we thought it should be. It's as if a substantial portion of the universe's fundamental building blocks has vanished into thin air. This isn't a small accounting error. It's a profound discrepancy that challenges our complete understanding of the cosmos's composition and how it evolved. Scientists have put forward a leading theory to explain this cosmic disappearing act. The missing baryons are believed to reside in a vast, diffuse network of gas known as the warm-hot intergalactic medium, or WIM. Picture a cosmic web of faint, tenuous gas filaments stretching between galaxies, heated to temperatures ranging from hundreds of thousands to millions of degrees Celsius. This incredibly hot and diffuse nature makes the WIM exceedingly difficult to detect directly using traditional telescopes, as it doesn't emit light in easily observable wavelengths. It's like trying to find an almost invisible, incredibly faint fog spread across billions of light years. Despite its elusive nature, indirect evidence for the WIM has been slowly accumulating. Astronomers have searched for its spectral fingerprints by observing how light from distant quasars, incredibly bright beacons from the early universe, is absorbed as it passes through these suspected gas filaments. These subtle absorption lines, particularly those produced by highly ionized oxygen, hint at the presence of the WIM. However, these detections remain challenging, and we haven't yet accounted for all the missing matter with certainty. The idea that such a substantial portion of the universe's ordinary matter exists in this hidden, diffuse state challenges our inventory of cosmic constituents, pushing us to develop new observational techniques to finally pin down where all the baryonic matter is hiding. The resolution of this puzzle could fundamentally alter our understanding of how galaxies form and how the cosmic web developed over billions of years. Moving on to another cosmic riddle, we confront the astounding puzzle of supermassive black hole growth. Imagine our universe just a few 100 million years after the Big Bang, a mere cosmic infant. According to our current understanding, this period should have been a time of nascent stars and galaxies slowly beginning to coalesce. Yet, to our surprise, powerful telescopes have revealed the existence of colossal supermassive black holes, boasting masses billions of times that of our Sun, already thriving in this early cosmic epoch. This observation throws a significant wrench into our established models of black hole formation and evolution. The conventional wisdom dictates that black holes grow primarily by two methods: slowly accreting surrounding gas and dust, or by merging with other black holes. However, these mechanisms, while perfectly adequate for explaining the growth of less massive black holes over billions of years, simply don't cut it for these early universe behemoths. The sheer amount of time required for them to gorge themselves into such immense sizes, even at maximum efficiency, seems far longer than the short window available in the young cosmos. It's like discovering a fully grown adult sprinting a marathon just minutes after birth. This rapid, almost instantaneous maturation of supermassive black holes in the early universe points to several intriguing possibilities. One idea is that the early universe might have provided a far more efficient, even exotic, growth mechanism than we currently account for. Perhaps the dense, gas-rich environments of nascent galaxies offered an accelerated feeding ground, allowing these black holes to grow at rates unimaginable in today's more spread-out cosmos. Another compelling theory suggests the existence of heavy seed black holes. Rather than starting from the typical stellar mass black holes formed from collapsing massive stars, these early universe monsters might have begun their lives as much larger entities, possibly hundreds of thousands of times the Sun's mass. These heavy seeds could have formed through direct collapse of massive gas clouds, bypassing the stellar phase entirely, or through runaway collisions of stars in dense primordial star clusters. Such exotic formation scenarios would drastically reduce the time needed for them to reach their observed gargantuan sizes. The challenge then becomes identifying the precise conditions and processes that could have facilitated such rapid and massive initial formations. The existence of these colossal early universe monsters profoundly defies our established timelines for cosmic evolution, forcing us to re-evaluate the initial conditions and subsequent development of the most powerful gravitational engines in the cosmos. It's a compelling anomaly that demands new physics and new ways of thinking about how the universe's grandest structures came to be. Another gravitational enigma, often misunderstood and far grander in scale, is the Great Attractor. Imagine an invisible, immense gravitational anchor in the distant universe, relentlessly pulling not just our Milky Way, but also thousands of other galaxies towards it. This isn't just a gentle tug, it's a powerful cosmic current orchestrating the motion of an enormous swath of our local universe. Discovered through meticulous observations of galactic motion, its gravitational influence is undeniable, creating what astronomers call a bulk flow of galaxies. Yet, despite its profound impact on cosmic dynamics, the true identity and composition of the Great Attractor largely remain a mystery. The primary obstacle to understanding this cosmic leviathan lies in a region astronomers quaintly call the zone of avoidance. This is a vast band across the sky where the thick dust and myriad stars of our own Milky Way galaxy obscure our view of distant objects. It's like trying to see a faraway mountain range through a dense, glittering fog. The Great Attractor just so happens to reside directly behind this galactic curtain, making direct observation incredibly challenging. This means we largely infer its presence and characteristics from the way galaxies are moving, rather than by directly seeing what's doing the pulling. While its gravitational effects are well established, the exact nature of the mass causing this massive pull is still debated. Is it an incredibly dense supercluster of galaxies, far larger and more concentrated than any we've seen before? Or could it be something even more exotic, perhaps a colossal concentration of dark matter, pulling everything towards it without emitting any light? Current theories lean towards a supercluster, possibly containing hundreds of thousands of galaxies, but the precise details of its structure and extent remain elusive. Some models suggest it might be part of an even larger structure, an interconnected web of cosmic filaments and nodes stretching across billions of light years. The pull of the Great Attractor demonstrates that our local corner of the universe isn't just expanding uniformly, it's also experiencing significant directional movement, a grand cosmic drift towards a powerful, unseen source of gravity. Understanding its true nature is crucial for mapping the large-scale structure of the universe and for refining our models of cosmic evolution. It challenges the assumption that gravity on these vast scales behaves precisely as we expect, prompting questions about the distribution of mass in the cosmos and the forces that shape galaxies over billions of years. What other hidden architectural wonders might be influencing the grand cosmic dance? Moving from the pull of massive, hidden structures, our next anomaly delves into the universe's total light output, specifically the puzzle of the extra-galactic background light problem. Imagine trying to measure all the light ever emitted by every star and galaxy throughout the entire history of the cosmos. This accumulated glow, known as the extra-galactic background light, or Hubble, is incredibly faint, akin to the faintest starlight on a moonless night, but stretched and diluted across billions of light years. Accurately measuring it is absolutely fundamental to understanding how galaxies formed and evolved, how many stars were born, and how much dust obscured their light over cosmic time. It's like trying to reconstruct the entire history of a bustling city by only looking at the collective glow of all its lights, both present and past. The challenge is that this EBL, by its very nature, is incredibly difficult to measure directly. It's a pervasive cosmic glow that our instruments struggle to isolate from the much brighter foreground light sources within our own Milky Way galaxy, like scattered sunlight or the faint emission from our galaxy's own dust. Think of it as trying to see a tiny candle flame from miles away during a fireworks display. The overwhelming brilliance of nearby sources simply drowns it out. Because of this, astronomers have to rely on a different, more indirect method to estimate the EBL, one that involves observing high-energy gamma rays from distant blazars, which are active galactic nuclei with powerful jets pointed directly at Earth. These ultra-energetic gamma rays, as they travel across billions of light years of intergalactic space, interact with the much lower energy EBL photons. When a gamma-ray photon collides with an EBL photon, it can produce an electron-positron pair, effectively attenuating or dimming the gamma-ray signal. The amount of this dimming or attenuation depends directly on the density of the EBL along the gamma ray's path. So, by measuring how much these blazar gamma rays are attenuated, scientists can then infer the total amount of EBL present in the universe. It's a clever trick using the gamma rays as cosmic probes to map out the invisible sea of light. However, here's where the anomaly creeps in. When astronomers perform these indirect measurements using gamma ray attenuation, they consistently find a higher amount of extragalactic background light than what they predict based on simply adding up all the light from all the known and observed stars and galaxies throughout cosmic history. This perplexing discrepancy, often greater than what can be explained by uncertainties in the measurements, suggests that there's more light out there than our current models of star formation and galaxy evolution can account for. It's as if we've meticulously counted every visible light bulb in our cosmic city, but the overall glow is still brighter than our tally suggests, implying some hidden, unknown sources of illumination. This missing light poses a significant challenge to our understanding of the universe's total star formation history. Could it be that our estimates of star formation rates in the early universe are too low? Or perhaps there are populations of faint, undetected galaxies or stars that are contributing to this cosmic glow. Some theories even propose more exotic explanations, such as unknown mechanisms affecting how light propagates over vast cosmic distances, or perhaps even new, undiscovered sources of light altogether. The extragalactic background light problem forces us to reconsider whether our inventory of the universe's luminous components is truly complete, and it pushes us to refine our models of how the cosmos has been lit up over billions of years. Moving from the puzzle of the universe's total light output, our journey through cosmic anomalies now brings us to some truly colossal structures that challenge our very understanding of how the universe is organized, very large-scale structures. Imagine the cosmos not as a smoothly distributed, even expanse, but as a vast, intricate cosmic web. This web is composed of immense filaments of galaxies and clusters, separated by enormous, relatively empty regions called voids. Our standard cosmological models, built upon the cosmological principle, predict that while there should be some clumping and structure on sufficiently large scales, the universe should appear roughly homogeneous and isotropic, meaning it looks pretty much the same in every direction. However, some recent discoveries of truly gigantic structures are pushing the boundaries of this assumption, causing us to question if our universe is quite as uniform as we once believed. Take, for instance, the Hercules Corona Borealis Great Wall. Discovered in 2013, this monumental structure is a vast group of galaxies and active galactic nuclei, spanning an astounding 10 billion light-years across. To put that into perspective, the entire observable universe is estimated to be about 93 billion light-years in diameter. This single structure is so incredibly large that it stretches across more than 1/10 of the width of the entire observable cosmos. Its sheer size is astonishing and presents a significant challenge to the cosmological principle, which suggests that structures of this magnitude should not exist within the age of the universe. According to our current understanding based on the Big Bang and the amount of time since then, gravity simply has not had enough time to pull matter together into such an immense, coherent formation over such vast distances. Another striking example is the Sloan Great Wall, discovered earlier in 2003. While not quite as large as Hercules Corona Borealis, it still stretches a staggering 1.37 billion light-years in length. This immense filament of galaxies was, for a time, considered the largest known structure in the universe. Its discovery provided some of the first strong observational evidence that the universe is indeed structured in a web-like fashion, with galaxies congregating along vast filaments. However, even this structure pushes the limits of what our cosmological models can easily explain regarding how quickly and efficiently matter could have assembled into such a large concentration. The existence of these structures, both the Hercules Corona Borealis and the Sloan Great Wall, forces us to re-evaluate the scale at which cosmic homogeneity truly applies. The implications of these very large-scale structures are profound. If the universe truly isn't homogeneous on these scales, it could mean that our fundamental cosmological models, particularly those describing the initial conditions and evolution of the universe, need significant revision. It might suggest that the early universe had larger density fluctuations than we currently assume, or that there are subtle anisotropies or preferred directions built into the very fabric of spacetime that influence how matter distributes itself. Some proposed explanations even venture into the realm of modified gravity theories, suggesting that gravity might behave differently on these immense cosmic scales, allowing for faster or more efficient structure formation. These cosmic megastructures defy expectations for uniformity, painting a picture of a universe that is far more complex and perhaps less uniform than our theories currently allow, urging us to explore new physics to fully comprehend their existence. Building on the idea that the universe might not be as uniform as we once thought, let's turn our attention to an anomaly that could reveal one of cosmology's greatest secrets, right here in our own cosmic neighborhood. We're talking about the intriguing observations of gamma rays emanating from the very center of our Milky Way galaxy. Scientists have detected an unexpected surplus of these high-energy photons, a phenomenon dubbed the GV excess. Now, what makes this excess so compelling is that known astrophysical sources, like pulsars or supernova remnants, struggle to fully explain its presence and distribution. If you map out where these extra gamma rays are coming from, they seem to be concentrated precisely where we expect a significant amount of dark matter to reside, the dense central halo of our galaxy. This is where it gets truly exciting. The observed pattern of the GV excess aligns remarkably well with theoretical predictions for the annihilation of weakly interacting massive particles, or WIMP. For years, WIMP have been a leading candidate for dark matter. The idea is that if these invisible particles exist, they might occasionally collide with each other, annihilating and releasing energy in the form of gamma rays. So, the gamma ray excess from the galactic center could actually be the debris of dark matter particles destroying each other, a faint but persistent echo of their invisible presence. If this interpretation were confirmed, it would be nothing short of a monumental discovery, the first direct detection of dark matter, a substance that has eluded us for decades despite its profound gravitational influence on the cosmos. This would revolutionize our understanding of the universe's composition and potentially unlock an entirely new sector of particle physics. However, the scientific community remains cautiously optimistic. While the WIMP annihilation hypothesis is compelling, other, more conventional astrophysical explanations cannot be entirely dismissed. One prominent alternative suggests that the GV excess might be due to a population of unresolved pulsars rapidly spinning neutron stars in the galactic center. These pulsars are known to emit gamma rays, and if there are many of them individually too dim for us to resolve with current telescopes, their collective emission could mimic the dark matter signal. Distinguishing between these possibilities requires more detailed observations and sophisticated analysis. Scientists are meticulously working to separate these astrophysical foregrounds from a potential dark matter signal, a task akin to finding a single new melody in a crowded, noisy concert hall. It's a challenging endeavor, but the stakes are incredibly high. The significance of the GV excess extends far beyond just identifying the source of some gamma rays. It offers a tantalizing hint of dark matter lurking right in our own cosmic backyard, rather than just being an abstract concept inferred from distant galactic rotations or cosmic background radiation. If we could definitively confirm that this signal is indeed from dark matter, it would provide crucial insights into its particle nature, allowing us to finally understand what this mysterious substance is made of. It could tell us about its mass, how it interacts with itself, and how it fits into the broader framework of fundamental physics. This potential breakthrough holds the key to revealing dark matter's true nature, moving it from a hypothetical necessity to a tangible component of our universe. Shifting our gaze from the invisible to the overwhelmingly luminous, we encounter our 18th anomaly, the puzzling discrepancy in stellar masses. For decades, astronomers have refined models that describe how stars form, live, and die based on fundamental physics. These models predict the maximum size a star can achieve before its own gravity tears it apart or it collapses into a black hole. However, recent observations, particularly of stars in the early universe or in extreme cosmic environments, suggest some stars might be far more massive than these established models allow. Imagine trying to build a skyscraper only to find some of the materials you're using are much lighter or heavier than your blueprints indicate. That is essentially what astronomers are facing with these supermassive stars. We're talking about stars that appear to be hundreds or even 1,000 times the mass of our own Sun. Current stellar evolution theory generally caps stellar masses at around 150 to 200 solar masses, beyond which the star's immense radiation pressure is thought to prevent further accretion of gas. Yet, evidence continues to mount for objects that blow past these limits. This is what we call the stellar mass problem, and it challenges the very bedrock of our understanding of stellar physics. So, how could these colossal stars come into existence? One possibility is that our understanding of the initial conditions for star formation, especially in the chaotic early universe, is incomplete. The early cosmos was a very different place, filled with primordial gas and lacking the heavy elements that cool gas clouds today. This might have allowed for much larger gas clouds to collapse directly into incredibly massive stars. Another idea involves different accretion rates. Perhaps, under certain extreme conditions, stars can gobble up surrounding gas and dust far more efficiently than our models predict, enabling them to accumulate mass at an unprecedented rate. Think of a cosmic vacuum cleaner sucking in vast amounts of material at breakneck speeds. Then there is the intriguing concept of stellar mergers. While individual stars might struggle to reach these extreme masses through accretion alone, several smaller, massive stars forming in a tight cluster could potentially collide and merge, building up to truly gargantuan proportions. This scenario would be more likely in the dense, crowded environments of early star-forming regions or in the cores of superstar clusters. Such events, though rare, could explain the presence of these extreme outliers, providing a pathway to stellar behemoths that defy our standard formation narratives. The implications of this anomaly are significant. If stars can indeed grow far larger than we currently believe, it would force us to rethink a cascade of astronomical phenomena. The life cycles of these supermassive stars are likely very different, impacting everything from the production of heavy elements in the universe which are forged in stellar interiors and supernovae to the formation of the first black holes. These colossal stars would have shorter, more violent lives, potentially leading to different types of supernova or even direct collapse into black holes, bypassing the supernova stage entirely. This could then influence the seeding of supermassive black holes in galactic centers, tying this anomaly back to another cosmic mystery we discussed earlier. Unraveling the secrets of these massive stars could provide crucial pieces to the grand puzzle of cosmic evolution, reshaping our understanding of the universe's chemical enrichment and the origins of its most extreme objects. Moving from the colossal stars within our cosmic neighborhood, we now turn our attention to something even grander: the potential for vast, unseen forces influencing the very motion of galaxies across immense cosmic scales. This brings us to the 19th anomaly, an intriguing concept once known as the dark flow. Before we fully grasp the power of the Great Attractor, which we discussed earlier, some astronomers observed a peculiar, non-random bulk motion of galaxy clusters. It was as if these massive collections of galaxies were all being tugged in a specific direction, beyond what could be explained by the gravitational pull of all the visible matter within our observable universe. Imagine a giant, invisible current in the ocean, subtly pulling a vast fleet of ships in one direction, even though there are no visible winds or tides to account for it. That is essentially what the idea of dark flow suggested. This hypothesized influence pointed to something beyond our cosmological horizon, structures or regions of mass that are currently unobservable but still exerting a gravitational pull on everything we can see. If this dark flow were confirmed, it would imply external gravitational pulls on our entire observable universe, meaning there's something out there, far beyond the reach of our telescopes, that is still shaping the cosmos we inhabit. Think of it as a cosmic puppeteer pulling strings we can't fully see. While more recent data has largely cast doubt on the statistical significance of dark flow, suggesting that the initial observations might have been statistical flukes or misinterpreted, the concept itself remains incredibly thought-provoking. The very idea that our observable universe might not be the whole story, but rather a tiny part of a much larger, gravitationally interconnected cosmic tapestry, challenges the very boundaries of our observable cosmos. It hints at influences from beyond, compelling us to consider whether the universe extends far beyond what our most powerful instruments can detect. Even if the evidence for dark flow has waned, the questions it raised about the true extent and influences on our universe continue to resonate, reminding us that there might be cosmic architects at play far beyond our current view. It pushes us to contemplate whether our cosmic island is part of a much larger, unseen continent. From the subtle, almost imperceptible tug of dark flow, we now shift our gaze to another profound mystery, one etched into the very fabric of time itself. This brings us to the 20th anomaly on our list, the baffling case of globular clusters that seem to be older than the universe they inhabit. Imagine looking at a family album and finding a photograph of your great-great-grandparent, but the picture itself is dated a decade before their birth. That's essentially the cosmic conundrum presented by these ancient stellar collections. Globular clusters are incredibly dense, spherical collections of hundreds of thousands, sometimes millions of stars, all bound together by gravity. They are like cosmic fossils containing some of the oldest stars in our galaxy, serving as crucial benchmarks for dating the universe. Scientists determine their age by studying the types of stars they contain and how those stars have evolved. The most massive and luminous stars burn through their fuel quickly and die young, while smaller, cooler stars live for billions of years. By observing which stars are still on the main sequence, the phase where stars proverbially spend most of their lives and which have evolved into red giants or white dwarfs, astronomers can estimate the cluster's age. It's a bit like a cosmic clock ticking down based on stellar lifetimes. For years, some of these stellar clocks seem to contradict our best estimates for the age of the cosmos. Our current universally accepted age for the universe, based on precise measurements of the cosmic microwave background radiation and the expansion rate, stands at approximately 13.8 billion years. However, early calculations for some of the oldest globular clusters, like Messier 5 and Messier 92, consistently yielded ages closer to 14 or even 16 billion years. This presented a stark and unsettling paradox. How could a cluster of stars be older than the universe in which it formed? It was a direct challenge to the very foundation of our cosmological timeline, forcing scientists to scrutinize every assumption built into their models. This age problem forced a critical re-evaluation on multiple fronts. Was our understanding of stellar evolution flawed? Perhaps stars in these dense environments behaved differently, or perhaps our models for the nuclear fusion processes within them needed refinement. Every variable, from the initial chemical composition of the stars to the precise distances and luminosities, was meticulously re-examined. Simultaneously, cosmologists revisited the measurements that determined the universe's age. Could the Hubble constant, which describes the universe's expansion rate, be slightly different? Or were there other hidden factors influencing our interpretation of the cosmic microwave background? Over time, advancements in observational astronomy, especially with instruments like the Hubble Space Telescope, and more sophisticated stellar evolution models have significantly narrowed these discrepancies. Better data and more refined physics have largely brought the estimated ages of most globular clusters into agreement with the universe's age. For example, improved understanding of convection processes within stars and more accurate distance measurements help chip away at the excess age. This has been a testament to the scientific process, identifying an anomaly, rigorously testing hypotheses, and refining our understanding. Yet, even with these advancements, a few persistent outliers remain, or the margin of error still allows for some clusters to hover on the edge of too old. These subtle, lingering inconsistencies, even if statistically marginal, keep the question alive: could these ancient stellar relics still hold some secret? Are they whispering clues about a slightly different cosmic timeline, a subtle adjustment to the Hubble constant, or even something more fundamental about stellar physics that we haven't fully grasped? The potential remains that these seemingly minor discrepancies could, in fact, be pointing towards a need for subtle adjustments in our cosmological models or our understanding of stellar evolution. They serve as a powerful reminder that even our most robust models are continually subject to refinement and revision as we gather more precise data. Moving on from the enigmatic ages of ancient star clusters, our cosmic journey now brings us to the 21st anomaly, the perplexing distribution of quasars. These aren't just any celestial objects. Quasars stand as some of the most extraordinarily luminous and energetic phenomena in the universe, essentially supermassive black holes at the hearts of active galaxies, greedily devouring vast amounts of matter. This insatiable appetite releases an incredible amount of radiation, making them beacons visible across billions of light years. Because they're so bright, we can observe them even from the most distant reaches of the cosmos, acting as cosmic flashlights that illuminate the early universe. For a long time, the prevailing scientific consensus positioned quasars primarily in the early universe. Our models suggested that these cosmic powerhouses were most prevalent when the universe was young and dense, providing abundant fuel for their central black holes. We therefore expected to find them predominantly at high redshifts, which in cosmology directly correlates with great distance and thus a view into the past. High redshift means the light from these quasars has been stretched by the universe's expansion, shifting towards the red end of the electromagnetic spectrum. Finding a quasar with a high redshift is like discovering an ancient fossil. It tells us about conditions billions of years ago. However, as our observational capabilities have grown, especially with more sensitive telescopes and sophisticated survey techniques, we've begun to encounter unexpected patterns in quasar distribution that don't quite fit this neat picture. While the vast majority still reside in the distant, early cosmos, astronomers have occasionally detected quasars at lower redshifts than theoretically predicted. This isn't just a minor statistical blip. It suggests that the conditions for forming and sustaining these energy-guzzling black holes might persist longer or arise again in the more mature universe than our current models would allow. Even more intriguing is the way some quasars are clustered in space. Our standard cosmological model, which describes the large-scale structure of the universe, predicts certain patterns for how galaxies and their embedded quasars should group together. Yet, there have been observations of unusual alignments or gravitational lensing events involving quasars that are surprising. Imagine finding a perfect row of 5 streetlights in a sprawling, random city. It just doesn't quite fit the expected chaos. These unforeseen arrangements raise questions about the underlying assumptions in our models of how large-scale structures form and evolve in the universe. Are there unknown forces at play that influence their positioning, or are our maps of cosmic structure formation missing a crucial piece? Perhaps the most puzzling aspect of quasar distribution is the occasional discovery of quasars that appear to be in close proximity to galaxies or other quasars, but at vastly different redshifts. If 2 objects are physically close in space, their light should have traveled for roughly the same amount of time to reach us, meaning they should have similar redshifts. When objects with significantly different redshifts seem to be physically associated, it challenges our understanding of distance measurements and the very nature of redshift as a reliable indicator of cosmic distance. Could this imply that some quasars are not as far away as their redshift suggests, or that there's an entirely new phenomenon at play affecting the light from these distant sources? The implications of these anomalies are profound. If our understanding of quasar formation and evolution is incomplete, it could mean our picture of how supermassive black holes grew in the early universe needs a significant overhaul. If their clustering patterns defy predictions, it hints at gaps in our knowledge of the cosmic web and how matter distributed itself after the Big Bang. And if redshift isn't always a straightforward indicator of distance, then a cornerstone of modern cosmology could be shaken. The enigmatic distribution of quasars, therefore, offers invaluable clues to the universe's energetic, formative phases, prompting a cascade of new questions about their true nature and the fundamental workings of our cosmos. Moving from the puzzling distribution of quasars, we now turn our attention to the 22nd anomaly, the astonishingly rapid formation of early galaxies. Imagine the universe as a vast cosmic ocean, just a few 100 million years after the Big Bang. According to our long-held models, at this incredibly young age, we expected to see only nascent puddles of gas and dust, just beginning to coalesce into the very first small and disorganized proto-galaxies. The process of building a massive galaxy with billions of stars and complex structures like spiral arms was thought to be a slow, painstaking affair, requiring billions of years of mergers and accretion. Cosmic evolution, we believed, was a gradual climb from simplicity to complexity. However, recent groundbreaking observations, especially those from the James Webb Space Telescope, have fundamentally challenged this tidy picture. We've begun to discover what appear to be fully formed massive galaxies, sometimes even with discernible spiral or disk-like structures, existing mere hundreds of millions of years after the Big Bang. To put that into perspective, if the universe's entire history were compressed into a single calendar year, these galaxies would be appearing in the first few days of January. These aren't just tiny stellar nurseries. Some of them are surprisingly large, comparable in mass to our own Milky Way galaxy, which has had nearly 14 billion years to grow. This early galaxy problem, or massive galaxy problem, forces us to ask a profound question: how did cosmic structures grow so rapidly in their infancy? How did these colossal celestial cities rise so quickly from the cosmic dust? The existence of these mature, massive galaxies in the early universe presents a significant hurdle for our current theories of galaxy formation and evolution. Our models typically start with tiny density fluctuations in the early universe, which gravitationally attract more matter over vast stretches of cosmic time, slowly building up larger and larger structures. This hierarchical formation model suggests that smaller galaxies form first, eventually merging to create larger ones, but these newly discovered behemoths seem to skip several steps, appearing almost fully fledged. It's like finding a fully grown oak tree just weeks after planting an acorn. This discrepancy suggests that either the initial conditions of the early universe were far more conducive to rapid galaxy growth than we thought, or that the mechanisms of star formation and galaxy assembly were dramatically more efficient in those nascent cosmic epochs. One possibility is that the early universe had larger initial density fluctuations than standard cosmological models predict. If some regions were born with significantly higher concentrations of matter, they would have had a head start in gravitationally collapsing and forming stars, accelerating the entire galaxy formation process. Another idea revolves around more efficient star formation. Perhaps the gas in the early universe was much colder or denser, allowing stars to form at an unprecedented rate, quickly building up galactic stellar populations. Or maybe these early galaxies consumed gas and merged with other smaller structures at a much faster pace than we currently account for in our simulations. The sheer abundance of available pristine gas in the early universe could have provided the necessary fuel for such explosive growth, leading to a much more accelerated assembly line for galaxies than previously imagined. Furthermore, these discoveries could imply that our understanding of the very first stars, known as population 3 stars, is incomplete. These hypothetical stars, formed from the primordial hydrogen and helium left over from the Big Bang, are thought to have been much more massive and short-lived than later generations of stars. Their explosive deaths as supernovas would have enriched the surrounding gas with heavier elements, paving the way for the formation of later stars and galaxies. If these first stars were even more efficient at producing and distributing these elements, it could have jump-started galaxy formation in an unexpected way. Understanding how these massive, early galaxies came to be is crucial, as they likely played a pivotal role in shaping the evolution of the universe, influencing the distribution of matter, the reionization of the cosmos, and the emergence of all subsequent cosmic structures. Their existence pushes the limits of how quickly structures could have assembled after the Big Bang, forcing cosmologists to re-evaluate the timelines of cosmic evolution and search for new physics that could explain these surprisingly mature celestial bodies. From the rapid rise of early galaxies, we now pivot to another intriguing anomaly: the theoretical existence of cosmic strings and textures. Imagine the universe in its very earliest moments, undergoing a series of dramatic phase transitions, similar to how water freezes into ice. Just as ice can develop cracks and defects as it solidifies, the incredibly dense and hot primordial soup of the very early universe might have formed what physicists call topological defects. These are stable, localized configurations of matter or energy that persist even as the universe expands and cools. Among the most fascinating of these hypothesized relics are cosmic strings and textures. Cosmic strings are often envisioned as incredibly thin, one-dimensional lines of pure energy, thinner than an atom but stretching across vast cosmic distances. If they exist, they would be remnants of a profound symmetry breaking that occurred fractions of a second after the Big Bang, when a fundamental force separated from the others. These strings wouldn't be made of ordinary matter, but rather would be incredibly dense, carrying immense tension, so much that a segment just a few miles long could weigh more than the Earth. They would ripple through the fabric of space-time, generating unique gravitational effects. Textures, on the other hand, are more complex, unstable defects, often described as knot-like structures in space-time that would quickly unravel, but in doing so, they could leave a distinctive signature on the cosmic microwave background. Although these cosmic strings and textures have never been directly observed, their existence would leave very specific and unique imprints on the universe, particularly on the cosmic microwave background, the ancient afterglow of the Big Bang. For example, a cosmic string passing between us and the CMB would subtly distort the light, creating a characteristic double image of objects behind it, or leaving a very specific pattern of temperature fluctuations. Researchers have painstakingly analyzed CMB data, looking for these telltale patterns such as sharp, linear discontinuities in temperature, but so far, these searches have not yielded definitive evidence. Beyond the CMB, these theoretical defects could also generate gravitational waves. While our current gravitational wave detectors are tuned to higher frequencies, primarily from merging black holes and neutron stars, a network of cosmic strings oscillating and colliding could produce a pervasive background of gravitational waves at much lower frequencies. The ongoing search for this primordial gravitational wave background using pulsar timing arrays offers another potential avenue for detecting these elusive structures. If detected, these waves would be a direct echo from the universe's infancy, providing an unprecedented window into the physics of the Planck epoch, an era of extreme energy and density that current particle accelerators can't even dream of replicating. The significance of finding cosmic strings or textures would be profound. Their detection would not only confirm theories about the universe's earliest moments and phase transitions, but could also provide vital clues about fundamental physics at energies far beyond what our most powerful particle accelerators can achieve. They could reveal hidden dimensions, new fundamental forces, or properties of spacetime that we currently have no way of probing. The subtle effects of these potential spacetime wrinkles, etched into the fabric of the cosmos, could truly unlock secrets about the universe's most extreme and mysterious origins, offering insights into the very nature of reality itself. Shifting from the subtle imprints of cosmic strings, we now turn our attention to another profound mystery, the gravitational wave background. We've all heard the incredible news of individual gravitational wave events, those powerful ripples in spacetime caused by the cataclysmic mergers of black holes and neutron stars. These detections, made by observatories like LIGO and Virgo, have opened up an entirely new way to observe the universe, moving beyond light to hear the cosmic symphony of spacetime itself. But these are just the loudest, most dramatic notes in a much grander, all-encompassing cosmic chorus. Cosmological models predict the existence of a pervasive gravitational wave background, a continuous hum of spacetime ripples originating from countless sources throughout the universe's history. Imagine it like the constant murmur of a distant crowd where you can't distinguish individual voices, but you know a multitude is present. This background isn't made up of just the mergers we can detect individually. It's also composed of gravitational waves from sources too faint, too numerous, or too far away to resolve on their own, from the very earliest moments of the universe to ongoing astrophysical processes. It's the universe's own background noise, a constant vibration that, if precisely measured, could unlock secrets about events that happened long before the first star ever shone. One of the most exciting aspects of this gravitational wave background is its potential to act as a cosmic echo chamber, revealing signatures of the early universe. The conditions just moments after the Big Bang were incredibly extreme, with energies and densities far beyond anything we can recreate in laboratories. Phase transitions similar to those that might have formed cosmic strings would have occurred, potentially generating a unique signature of gravitational waves. These primordial waves would have streamed through the universe unimpeded, carrying information about an era shrouded in mystery, an era before light could even travel freely. By carefully analyzing the properties of this background, scientists could uncover direct evidence of these ancient cosmic events. The search for this elusive background is primarily focused on very low-frequency gravitational waves, often in the nanohertz range, which are far too long for ground-based detectors like LIGO to pick up. Instead, scientists are using an ingenious technique called pulsar timing arrays. Pulsars are rapidly spinning neutron stars that emit incredibly precise beams of radio waves, acting like cosmic lighthouses with highly stable clocks. If a gravitational wave passes between Earth and a pulsar, it subtly stretches and compresses the fabric of spacetime, causing tiny, measurable deviations in the arrival times of the pulsar's radio pulses. By monitoring a network of these pulsars across the galaxy and correlating their pulse variations, researchers hope to detect the faint, collective signature of the gravitational wave background. The precise measurement and characterization of this background would represent a monumental achievement in cosmology, offering an unparalleled window into the forces and conditions that shaped our cosmos from its very inception. It could confirm theories about the universe's rapid inflation immediately after the Big Bang, provide evidence for exotic phenomena like cosmic strings or primordial black holes, or even reveal entirely new physics that we haven't even conceived of yet. This cosmic hum holds the promise of an entirely new understanding of the universe's fundamental properties, allowing us to listen to the very whispers of creation. Moving from the echoes of creation in the gravitational wave background, we now peer into the universe's grand architecture itself, exploring the 25th anomaly, cosmic voids and walls. Imagine the universe not as a uniformly distributed soup of galaxies, but as a vast, intricate cosmic web. This network is made up of immense filaments of galaxies, known as walls, interspersed with colossal, nearly empty regions called voids. These structures are the largest known in the universe, stretching for hundreds of millions, sometimes even billions of light years. They are the natural outcome of gravity acting on tiny initial density fluctuations in the early universe, pulling matter together into these filamentary patterns and leaving behind the vast, underdense voids. In our standard cosmological models, particularly the lambda CDM model, the formation and distribution of these cosmic voids and walls are well understood, and simulations beautifully reproduce their general characteristics. They are the expected results of the universe's dance of expansion and gravitational collapse. However, despite this generally successful picture, the precise extent, distribution, and statistical properties of some of these cosmic voids and walls sometimes show subtle, yet significant, deviations from what our most advanced cosmological simulations predict. For example, some observed voids appear to be larger, emptier, or more sharply defined than expected, while some walls seem to be more robust or extend over greater distances. This isn't just a minor statistical blip. These deviations, when viewed collectively across various sky surveys, hint at a potential mismatch between our theoretical predictions and the actual universe. It's like having a blueprint for a magnificent skyscraper, but then finding that some of the actual floors or foundational beams are slightly different in size or placement than anticipated. These discrepancies challenge the assumption of homogeneity on very large scales, which is a fundamental tenet of our cosmological models, stating that the universe looks roughly the same everywhere when averaged over vast distances. The existence of these anomalous megastructures, particularly the largest voids or walls, could suggest subtly different initial conditions in the early universe than we currently assume. Perhaps the primordial density fluctuations that seeded these structures were not perfectly random or Gaussian, as our models generally assume, but had some unexpected biases or features. It's a tantalizing thought. The universe might have had a slightly different seed pattern at its birth, leading to these observable differences in its current large-scale arrangement. Alternatively, these deviations could point to something more exotic. Perhaps the nature of dark energy or dark matter isn't precisely what we think, and their subtle influence over billions of years has shaped these structures in ways our current models don't fully capture. The way galaxies cluster and voids expand are direct probes of these elusive cosmic ingredients, and any unexpected patterns could be a clue. Furthermore, these vast structures are not just static features. They are the result of dynamic processes over cosmic time, acting as the blueprints of cosmic evolution. Their precise architecture continues to surprise us because they represent the cumulative effect of every major cosmic event since the Big Bang. If our measurements of these voids and walls are accurate and the discrepancies persist, it forces us to re-examine our fundamental assumptions about how the universe evolved. It opens up possibilities for new physics, perhaps related to the very early moments of cosmic inflation, or perhaps even subtle modifications to the laws of gravity on truly immense scales. Unraveling the exact nature of these cosmic web anomalies could provide crucial insights, not just into the distribution of matter, but into the fundamental forces that sculpted the cosmos into the universe we observe today. These vast cosmic patterns serve as a profound test of our understanding of the universe's grand design. From the grand cosmic architecture of voids and walls, we now delve into an anomaly that challenges our understanding of beginnings themselves. This brings us to the 26th anomaly, primordial black holes. Imagine the universe just moments after the Big Bang, a swirling, incredibly dense, and unimaginably hot plasma. In this chaotic, primordial soup, small fluctuations in density were inevitable. While most of these fluctuations eventually smoothed out or formed the seeds of galaxies, some theories propose that under the right conditions, certain regions could have become so dense that they collapsed directly into black holes. These wouldn't be the stellar mass black holes we know today, formed from the collapse of massive stars, but rather ancient, microscopic, or even planet-sized black holes that came into existence before the very first stars even had a chance to ignite. They are truly relics of the universe's earliest infancy, holding within them the secrets of a time we can only theorize about. The concept of primordial black holes isn't just a fascinating theoretical exercise. It has profound implications for one of cosmology's greatest mysteries, dark matter. If these hypothetical black holes exist, they could potentially constitute a significant fraction, or even all, of the elusive dark matter that pervades our universe. For decades, scientists have been searching for dark matter in the form of exotic particles, but if it turns out to be made up of these ancient black holes, the entire search strategy would shift dramatically. Think about it. Instead of trying to detect tiny, weakly interacting particles, we would be searching for the gravitational signatures of these compact, invisible objects. Their existence would not only solve the dark matter puzzle, but also revolutionize our understanding of black hole formation. pushing their origins back to the very dawn of time, long before stars provided the necessary fuel. Could these ancient cosmic relics truly be the invisible scaffolding that shapes our universe? Furthermore, the existence of primordial black holes could also shed light on another groundbreaking discovery of recent years: gravitational waves. When two black holes merge, they send ripples through space-time that we can now detect here on Earth. The recent uptick in observed gravitational wave events has given us an unprecedented window into the cosmos. While many of these events are attributed to stellar mass black holes, some of the detected mergers involve black holes with masses that are difficult to explain through conventional stellar evolution, falling into a mass gap between neutron stars and larger stellar black holes. If primordial black holes exist, their mergers could perfectly explain some of these anomalous gravitational wave signals. Imagine ancient black holes, born in the Big Bang, wandering through the cosmos for billions of years before finally colliding, sending out echoes that reveal their primordial origins. This connection would provide a powerful, observable link to the universe's earliest moments, offering a direct test for their existence and allowing us to probe the universe's initial conditions in ways previously unimaginable. The pursuit of primordial black holes underscores the intricate connections between seemingly disparate cosmic phenomena. If we could detect and confirm their presence, it would not only be a monumental achievement in solving the dark matter mystery, but also open new avenues for understanding the extreme physics of the early universe. It forces us to consider that perhaps the most fundamental building blocks of our cosmos aren't just subatomic particles, but also these ancient, invisible gravitational behemoths. The implications are staggering, potentially reshaping our entire cosmological model and revealing a universe far more complex and ancient than we currently grasp. The search continues, and with every new gravitational wave detection or refined observation of the cosmos, we move closer to either confirming or ruling out the existence of these captivating relics from the very first moments of spacetime. From the grand cosmic architecture of voids and walls, we now delve into an anomaly that challenges our understanding of beginnings themselves. This brings us to the 26th anomaly: primordial black holes. Imagine the universe just moments after the Big Bang, a swirling, incredibly dense, and unimaginably hot plasma. In this chaotic, primordial soup, small fluctuations in density were inevitable. While most of these fluctuations eventually smoothed out or formed the seeds of galaxies, some theories propose that under the right conditions, certain regions could have become so dense that they collapsed directly into black holes. These wouldn't be the stellar mass black holes we know today, formed from the collapse of massive stars, but rather ancient, microscopic, or even planet-sized black holes that came into existence before the very first stars even had a chance to ignite. They are truly relics of the universe's earliest infancy, holding within them the secrets of a time we can only theorize about. The concept of primordial black holes isn't just a fascinating theoretical exercise. It has profound implications for one of cosmology's greatest mysteries: dark matter. If these hypothetical black holes exist, they could potentially constitute a significant fraction, or even all, of the elusive dark matter that pervades our universe. For decades, scientists have been searching for dark matter in the form of exotic particles, but if it turns out to be made up of these ancient black holes, the entire search strategy would shift dramatically. Think about it. Instead of trying to detect tiny, weakly interacting particles, we would be searching for the gravitational signatures of these compact, invisible objects. Their existence would not only solve the dark matter puzzle, but also revolutionize our understanding of black hole formation, pushing their origins back to the very dawn of time, long before stars provided the necessary fuel. Could these ancient cosmic relics truly be the invisible scaffolding that shapes our universe? Furthermore, the existence of primordial black holes could also shed light on another groundbreaking discovery of recent years: gravitational waves. When two black holes merge, they send ripples through spacetime that we can now detect here on Earth. The recent uptick in observed gravitational wave events has given us an unprecedented window into the cosmos. While many of these events are attributed to stellar mass black holes, some of the detected mergers involve black holes with masses that are difficult to explain through conventional stellar evolution, falling into a mass gap between neutron stars and larger stellar black holes. If primordial black holes exist, their mergers could perfectly explain some of these anomalous gravitational wave signals. Imagine ancient black holes, born in the Big Bang, wandering through the cosmos for billions of years before finally colliding, sending out echoes that reveal their primordial origins. This connection would provide a powerful, observable link to the universe's earliest moments, offering a direct test for their existence and allowing us to probe the universe's initial conditions in ways previously unimaginable. The pursuit of primordial black holes underscores the intricate connections between seemingly disparate cosmic phenomena. If we could detect and confirm their presence, it would not only be a monumental achievement in solving the dark matter mystery, but also open new avenues for understanding the extreme physics of the early universe. It forces us to consider that perhaps the most fundamental building blocks of our cosmos aren't just subatomic particles, but also these ancient, invisible gravitational behemoths. The implications are staggering, potentially reshaping our entire cosmological model and revealing a universe far more complex and ancient than we currently grasp. The search continues, and with every new gravitational wave detection or refined observation of the cosmos, we move closer to either confirming or ruling out the existence of these captivating relics from the very first moments of spacetime. This brings us to the 27th anomaly, the fine-tuning problem. As we delve deeper into the universe's fundamental properties, we encounter something truly astonishing. The laws and constants of physics appear to be exquisitely balanced for the existence of life. Consider the strength of gravity, for example. If it were even slightly stronger, stars would burn out much too quickly, leaving no time for life to evolve. If it were weaker, matter would never coalesce into stars and galaxies in the first place. This isn't just about gravity. It extends to the electromagnetic force, the masses of elementary particles, and even the initial conditions of the Big Bang. Scientists have identified numerous such parameters, each seemingly calibrated to a breathtaking degree of precision. Imagine a cosmic control panel with countless dials, and every single dial is set to just the right value to allow for the formation of atoms, the creation of complex chemistry, and ultimately, the emergence of conscious beings like us. This isn't a minor coincidence. It's a profound observation that challenges our understanding of the universe's inherent properties. The sheer improbability of this cosmic alignment gives rise to some of the most compelling and debated questions in modern cosmology. One perspective suggests there might be an underlying principle, a deeper law of physics yet to be discovered, that dictates these constants must be precisely what they are, making the universe's life-permitting properties a natural consequence rather than a fortunate accident. Another intriguing possibility points to the existence of a multiverse, a vast ensemble of universes, each with different physical laws and constants. In this scenario, our universe would simply be one of countless others, and it just happens to possess the specific conditions necessary for life to arise. Because we are here to observe it, we naturally find ourselves in a universe conducive to our existence. This idea elegantly sidesteps the need for fine-tuning by positing an infinite number of cosmic possibilities. Yet a third viewpoint, often embraced by theologians and some scientists, interprets this uncanny precision as evidence of purposeful design, suggesting a cosmic architect or creator. Each of these explanations presents a radically different picture of reality, from a universe governed by a yet unknown cosmic equation to an endless landscape of parallel worlds, or a cosmos imbued with inherent purpose. The fine-tuning problem is not merely a philosophical curiosity. It's a thorny scientific challenge that forces us to grapple with the very nature of existence. It pushes the boundaries of our current scientific models and demands a deeper explanation than simple chance. If the universe were not so precisely calibrated, there would be no stars, no planets, no carbon, and no way for complex structures to form. The fact that we are here contemplating these questions is itself a testament to this extraordinary cosmic precision. Whether it's a hidden law, a multiverse of possibilities, or something else entirely, unraveling the mystery of the universe's finely tuned constants promises to reshape our understanding of ultimate reality. It begs us to look beyond the observable mechanics and consider the profound question of why our universe is the way it is, in all its life-supporting glory. This uncanny cosmic precision truly begs for a deeper explanation, inviting us to ponder the very foundations of reality itself. This brings us to the 28th anomaly, the information paradox, centered around one of the universe's most enigmatic objects, the black hole. At its heart, this paradox pits two of the most successful theories in modern physics, quantum mechanics and general relativity, against each other. Imagine throwing a book or a person or an entire star into a black hole. According to Albert Einstein's theory of general relativity, once something crosses the event horizon, the point of no return, it's gone forever. The black hole simply adds to its mass and any unique characteristics or information about what fell in seem to vanish with it. Now, this is where quantum mechanics steps in with a fundamental rule. Information can never be truly destroyed. It might be scrambled or transformed, but its essence must always be preserved. Think of it like burning a piece of paper. The paper changes form, but all the information contained in its ashes and smoke could, in principle, be used to reconstruct the original paper. The black hole, however, appears to be a cosmic incinerator that not only burns the book but makes its details utterly irrecoverable. This fundamental clash between the apparent destruction of information by black holes and the quantum mechanical principle of information conservation is known as the information paradox. It's not just a theoretical squabble. It highlights a deep, underlying incompleteness in our understanding of the universe, particularly when it comes to extreme environments where quantum effects and gravity are both overwhelmingly strong. One of the key figures in this debate was Stephen Hawking, who theorized that black holes emit a faint thermal radiation, now known as Hawking radiation, which causes them to slowly evaporate over vast stretches of time. If a black hole eventually evaporates completely, and all the information that fell into it is truly lost, then quantum mechanics is fundamentally broken. Conversely, if information somehow escapes, even in a scrambled form, then our understanding of black hole event horizons and the fabric of spacetime itself needs a radical overhaul. This paradox is one of the most compelling reasons why physicists are desperately seeking a unified theory of quantum gravity, a grand theory that seamlessly merges general relativity's description of gravity with quantum mechanics rules for the subatomic world. The implications of resolving the information paradox are profound, reaching far beyond just black holes. A breakthrough here could reveal a path to understanding the universe at its most fundamental level, touching upon the very nature of reality, causality, and the conservation laws that govern existence. Various theoretical solutions have been proposed, each with its own set of mind-bending consequences. Some suggest that information is encoded on the event horizon itself, like a cosmic hologram, and slowly leaks out with Hawking radiation. Others posit that a black hole might leave behind a tiny, super-dense remnant containing all the initial information. Still, another radical idea suggests that information passes into another universe or a region of space-time inaccessible to us. The debate continues, fiercely contested by some of the brightest minds in physics, because the answer holds the key to reconciling the two pillars of modern physics and constructing a complete picture of the cosmos. Reconciling these two giants of physics is paramount for achieving a truly complete cosmic picture, one that accurately describes both the smallest particles and the largest structures in the universe, finally unraveling one of its deepest secrets. We've journeyed through 28 of the most baffling cosmic anomalies, each a testament to the universe's enduring mysteries and the limits of our current understanding. From the subtle, inexplicable tugs experienced by the Pioneer spacecraft as they ventured into the cosmic void, hinting at unknown forces, to the accelerating, pervasive push of dark energy, which dictates the very expansion of our cosmos, these puzzles are not merely academic curiosities or isolated scientific oddities. Instead, they stand as crucial signposts, beckoning us towards uncharted territories in physics and cosmology. They challenge us to reconsider assumptions that have long formed the bedrock of our scientific understanding, pushing the very boundaries of scientific inquiry and serving as a powerful, humbling reminder that the cosmos is far stranger and infinitely more complex than we can currently imagine. The relentless quest to solve these bewildering anomalies promises to reshape our cosmological models forever, dismantling old paradigms and illuminating a deeper, more profound cosmic truth. It is a journey that demands intellectual courage, innovative thinking, and a willingness to embrace the unknown as a frontier of discovery. This exploration into the universe's most profound secrets underscores a fundamental aspect of scientific progress, that every unanswered question is an invitation to new knowledge, every anomaly a clue to a grander, more accurate picture of reality. What new laws of physics await discovery as we unravel these enigmas? What hidden dimensions, unknown particles, or exotic interactions will emerge from the shadows of these cosmic puzzles? The impact of resolving these anomalies extends beyond academic curiosity. It could fundamentally alter our perception of space, time, gravity, and the very fabric of existence. Imagine a universe where gravity behaves differently on vast scales, or where the dark matter and dark energy that permeate everything are revealed to be manifestations of entirely new physical laws. Such revelations would not only satisfy our intellectual curiosity, but could also unlock technological advancements and philosophical insights currently beyond our grasp. The universe is speaking to us through these anomalies, whispering secrets that challenge our most cherished theories and inviting us to listen more closely, to observe with greater precision, and to think with unbounded imagination. As we conclude this journey through some of the universe's most perplexing questions, we encourage you, our curious explorers, to continue delving into these fascinating frontiers. Each anomaly we've discussed is a vibrant area of ongoing research, with new discoveries and theories emerging constantly. Your engagement with these ideas, your questions, and your own reflections are vital to the collective human endeavor of understanding the cosmos. Share your thoughts on which anomaly intrigues you most in the comments section below. Is it the missing matter, the accelerating expansion, or the paradox of information within black holes that most captures your imagination? Your insights help fuel the conversation and inspire further exploration into the boundless wonders of the universe.